Hello everyone. Welcome you all to week 8 problem solving session of the course Introduction to Group Theory offered by NPTEL. I'm Priyanka Sharma, the PMRF NPTEL teaching assistant of the course, and I'm a research scholar from the Indian Institute of Technology, Patna. Uh, so let's start this week's problem solving session. So the problems of this week is based on group action, which is a very powerful tool in abstract algebra. So first we recall the theory of the lectures of this week. First we understand what is a group action or how a group acting on some set. For this, we consider a group. So say G be a group and X, this is a non-empty set. Then we say that the group G is acting on X via some group homomorphism, this tau, which is symbolically denoted as G is acting on X sometimes. So, okay, we say that G is acting on X via some group homomorphism tau, which is a group homomorphism. So we need two groups. Okay. So here this X is a set. So we define a group using this set, and the set is the set of all permutations or the set of all bijections on this set X. Okay. So here we are taking this group Sx, which is the group of all functions from X to X such that F is a bijection. Okay. So we say that G acts on X if these conditions are satisfied. That is, for all G belongs to G, tau G, which is defined from X to X, this is a bijective map. Okay, so actually, this tau is a map from G to Sx. So in this way, we will have for each element G belongs to G, some tau G in Sx. So how this tau G will work in Sx? So for that, tau G, if this is in Sx, so this will be a bijective map on X. And okay, so how we define this tau G? So this tau G, this as this belongs to Sx, so this tau G will be a bijective map from X to X, and obviously we will have that tau G of X is say some Y for all X belongs to X. Okay, so this is the setup, and we will have these three conditions, that tau of identity, that is the Mm, that is the image of this group action tau with respect to the identity element E. This will give us the identity element of Sx. That is the identity map on X. That is, for all X belongs to X, we will have this one of X is X. Okay. The second condition is that tau of G inverse, this will be tau of G inverse. So if we simplify this, we will get the inverse of tau G. Here this tau of G inverse, this is an element of Sx. So for each element tau of G in Sx, we will have some tau of G inverse in Sx, which is same as the inverse of tau of G. Now, the another required condition is that tau of G1 and G2, where this G1 and G2 are two elements from the group capital G. So how we define this tau of G1, G2? Tau of G1, G2 is actually the composition of tau of G1 and tau of G2, as tau of G, this is in Sx. So Sx is a group where the group operation is the composition of maps. So that is why we are using this composition operator here. Okay. So, in short, we will say that to define a group action, first we need a group and a non-empty set. And then the group is said to be acting on the set X if we have some group homomorphism from the group to the permutation group of the given non-empty set, and the image of the identity element of G will give us the identity map on X, and tau of G1, G2. This is tau of G1 composed by tau of G2. Equivalently, we define this as, okay, so we say Gx on X via some phi from G cross X to X. This is an alternate way to define the group action. So here we use this product form like G cross X, and we need a map phi from G cross X to X, which is defined like this. That is the pair Gx. This is mapped on phi of Gx. So we say that the phi is a group action if the following conditions are satisfied. That is, okay, this one is equivalent to the first condition. That is, tau E is identity on X. So this is equivalent to say that phi of E comma X, this is X. Okay, that is, if we take identity element of the group G and any element from the set X, and if we perform the group action, which is phi, then we get the same element X in the set capital X. Okay, so this is the first condition for a map on G cross X to X be a group action. And the second condition is that phi of G1, G2, comma X. So here we are willing to define the group law. Okay, so this G1 and G2, obviously we can define this as G is a group. So G1, G2, comma X, this will be mapped on G1, comma phi of G2 X. So this is same as the composition rule here. Okay, so what we are doing here, if we want to uh, find the action of phi on the element X belongs to the set X via this group element G1, G2, then what will be the result? It will be actually this phi of G1 and phi of G2 G1 means the first this G2 will be performed on X. So first we will find the group action for this second element G2. Now this phi of G2X. So this will be an element in the set X by this map. Okay. So this is like some element in G and this is some element in X. So this is well defined in that sense. Okay. So whenever we have phi of G1, G2, comma X, so what we will do? First, we will find phi of G2X, and then that will become an element of X. So then we will compute phi of G1 and that element, that is phi of G2, comma X. So yeah, this is the equivalence in both the forms. Okay. So we can either write in this way or that way. Okay. So G1 comma X, that is we are taking elements of this product G1 cross X. So G1 cross G comma X, this will be mapped on phi of Gx, or we will have some tau of G and then we will have tau of G of X. Okay. So the first condition is a condition with respect to the identity element, and the second condition, which is called the group law. So this is corresponding to the composition. Now, uh, for a given phi, we can define tau from G cross from G to Sx such that tau of G, which is represented as tau of G actually, this is like this phi of G comma some element of X. So in this way, we can say that these two definitions, first one is with respect to some phi from G cross X to X, and second condition using tau notation, uh, that is a group homomorphism between G and Sx. So these two are equivalent. Whenever we will have tau of G, so this is actually tau of G of X. This will be same as phi of G comma X for all X belongs to the given non-empty set X. Okay. So these two are same, like tau G is same as phi. Uh, okay. Now this is the notation we will use further. So if we have a group homomorphism tau from G to Sx, where this group G is acting on the set X, then how we denote it? Tau G of X, this will be represented as G dot X. Here, this dot is actually the group action phi. Okay, is given for G dot X. That is phi is a product here. This is not the group operation on G. Okay, was G uh, X, they are coming from different kind of sets. So this is not a group operation of. Now we have some examples to understand this group action. So fine. Whenever we want to define some group action or we talk about the term group action, what we need? We need a group and a non-empty set on which the group is acting, and a map or some rule by the by which the group is acting on the set. Or we can say we need three things: a group which is acting, a non-empty set on which the group is acting, and a homomorphism, a group homomorphism between the given group and the group of permutations of the given set X. So these are some examples. Suppose this X, this is a given non-empty set, and G. So if we take G itself as a subset of Sx, then the inclusion map is obviously group homomorphism. This will be a group action. And this is how the group is acting. So for each G belongs to G, this will act on X as this G from X to X. This is given as this X is mapped onto Gx, which is G dot X. So this is like obvious example. So actually, we want to figure out groups and the sets. So in the first example, what we did, uh, the non-empty set X, we pick that as any arbitrary non-empty set, and the group that is chosen as some subgroup of the permutation group of the given set X. In the second example, we are taking the group and the non-empty set both as same. That is, a group can act on itself. This is again some kind of obvious thing, because whenever we want to define a group, we start it from some non-empty set at initial. Okay. So obviously, if we have a group, the group is a non-empty set. So why can't we think that the group can act on itself also? So yes, it it can be figured out. It is true actually. So a group does act on itself via the multiplication. How we define it? So tau from G to SG, that is the group of all permutations or the group of by from G defined like this. G is tau of G and tau of G of X. This is Gx sim. Now note that this G is an element of G and this X, this is also an element of G. So here this Gx, they are uh, being operated using the group operation itself. So here the multiplication is the group operation. Okay. Third example, the group acting on itself via conjugation. So how we define the conjugation for something? So suppose we have um a group G and we have an element X belongs to G, then conjugation of X, this is defined as GX G inverse for some G belongs to G. And if we have some subgroup of G, then conjugation of this H, this is defined as GHG. So this is the way of defining the conjugation. And yeah, this is useful if we have a non-abelian group precisely. Otherwise, this conjugation will give us the trivial thing. Okay, as the elements will commute in that case. So, okay, we want to define a group action via the conjugation, like this thing. So we fix some G belongs to G, and we define the conjugation with respect to this fixed element G in G. So CG, which is defined from G to G, this is a bijection such that X is mapped onto GX G inverse. Then, so this is, yes, okay. So this is the way to define conjugation map. Now, this is the group action. This C, this is the group action, or like we can say this is tau of G. If we want to align this with the notation we used in the definitions. So C, this is a group action if the group G is acting on G itself. So C is a group homomorphism from G to SG. And how we define this? By the conjugation. That is, each element G is mapped onto conjugation of element of G with respect to G by fixing this. So this is also a group action. Another example. So again, suppose we have a group, say G, and capital V, which is a vector space over some field F. And if we have this like G, which is a subgroup of GLV, which is again a subgroup of SV, that is the permutation group of the vector space V, then by this inclusion map, we will again get a group action. Here, the group G is acting on the non-empty set V, which is further a vector space over F, by the group action inclusion. This notation, this is the notation for inclusion. And here we can use the inclusion because this GLV and SV, they are like comparable. Like the elements are of same types. We are taking the subset notation there. So that is well defined here. Now the another example. If we take H, which is a Okay. So first, this G is a group, and this H, this is another group. So if G, this is a subgroup of the group of automorphisms of H, which is further in subgroup of SH. See here, what is SH? SH is the group of all bijections uh, on H. Okay, so here we are taking all 1, 1 and on 2 maps. And here we are taking automorphisms. That is the maps which are 1, 1 on 2 as well as homomorphism, actually endomorphism, as we are taking maps from H to itself. So yeah, this is trivial that like this is obvious. We can prove it that the group of automorphisms of a given group H, this is a subgroup of the permutation group of H. So this is true. And if we take the group which we are willing to define some action. So if G is defined like this is a subgroup of the group of automorphism on H, then again we can define the inclusion map because by transitivity, G is a subgroup of SH. So we can define a group action where the group is G and the non-empty set is another group H. See here, the group operations of H and G, they can be different. H and G can be non-comparable, obviously. But we can have a inclusion map because G and SH, they are comparable as G is a subgroup of SH. So that's why we can define this. Okay. So for a given group and for a given group as a non-empty set, the inclusion map is a group action if the group is a subset of the group of automorphism of the given group H. Okay. Another example, suppose we have a group, say G, and this time we are taking this H as a subgroup of G explicitly. Okay. So if G is a group and H is a subgroup of G, then we define the non-empty set X by this G mod H, which is the set of left cosets of H in G. That is the collection of this XH, where X are coming from G. Okay, so this is the set of all left cosets of H in G. Then we define the group action by this notation LH, and this will be a group homomorphism from the group G to SX. Here, this X is G mod H. Okay, so this is defined such that, uh, okay, let me write it again. Mm, we have group action mm, from the group G on the set X. And obviously, then we will have a group homomorphism from G to SX. So every G will be mapped onto some LHG will be a map on this. Okay. So this will be a bijective map from X to X. Okay. And how we define this? We define this by this rule, that is XH. This will be mapped on GXH. What is G here? G is this. That is, what we will say? We'll say that LHG of X, this will be GXH. This is again a group action. Seventh, suppose we have a group and a subgroup of it. Then, yeah, this time we are taking conjugation of a subgroup. In another example, this one. In example 3, we take conjugation of an element. Okay. By that, we define a group action, and the group action was the conjugation map actually. And in this example, we are defining the group action using the conjugation of a subgroup. So G is a group, H is a subgroup of G, and what will be the non-empty set X on which we want to define the group action? That is the um, conjugation. Okay, so X is the collection of G, H, G inverse, where this H is a fixed subgroup of the group G, and this G is an element of G. Okay. Then we define this CH, which is a group homomorphism from G to SX, and this will map any G to CHG, and this CHG, this will be a bijection from X to X, such that CGH of XHX inverse, this will be given by this G XHX inverse G inverse. So yeah, we can verify the necessary and sufficient condition or the definition of group action here. So this CG inverse H, this is the inverse map of CGH, and obviously the group law is given by this. So here these two are bijective maps, so we will use the composition operator to define this group law here. Okay, so these are some examples of group action. Again, I want to recall what we need to define a group action. We need a group, we need a non-empty set, and we need a group homomorphism from the group to the permutation group of the non-empty set. Okay, three things. Again, I will say G, which is a group, X, which is a non-empty set, and some tau G, that is a group homomorphism from G to SX. This SX is the permutation group of X. These three things are required. Okay, then we say that the group G is acting on the set X via tau G. So this tau G is the group action, G is the group which is acting, and this X is the non-empty set on which the group G is acting. Okay. Now we define another important term, which is orbit. So orbit is defined for some element of the set X. Okay. Like we have two kind of algebraic structure here, a non-empty set mm, and a group G. So this orbit is defined for the elements of the given non-empty set using the group action, obviously. So, and to define this, what we assume, let G be a group and X be a non-empty set, and Gx on X via this um, group homomorphism tau from G to Sx. Now we fix an element x of x as we are willing to define its orbit. So the orbit of x, which is an element of x, this orbit is denoted by either like ORB of x or simply OX. So this is defined like this. Orbit of x is the collection of G dot x, where this G is coming from G. Okay, so obviously this orbit of x, that is this OX, this will be a part of the non-empty set X. Okay, because this Gx here, this G is in Gx. Here this G is coming from the group G and this X is coming from X. So write it a bit smaller. gx to x. So this g dot x, this is become an element of x now. Okay. So yeah, this is actually a part of x, we can say. So what is the orbit for a given element x? The orbit will be the collection of, we can say, uh, collection of all actions for elements of G on X. Okay. Now, if the group is finite, then the orbit will also be finite, because if the group is finite, then number of group elements will be finite. So the number of elements which can act on some given element X of capital X will be finite. That is, we will have a finite number of mm, tau G there. Now, how we define orbit decomposition for a given non-empty set X? So, this is the way. So, suppose we have a set X and we have an element X belongs to X, then we can define this like actions G dot X, H dot X, F dot X, and more. And for another, we will have for another element Y, we will have G dot Y, H dot Y, and so on. So this way we can partition the given set X. I'm using the term partition. What does it mean? Please be precise. Uh, Let me explain this. The set of union of orbits, that is this O of X, where this X is an element of X. This set forms a partition of the given set X. That is the union of all orbits. They will give us the entire set X. And for given two distinct elements X and Y in capital X, either their orbits are disjoint or their orbits are same. So this is uh, the definition of partition actually. It means we can use the orbits which we can obtain by some group action to decompose a given non-empty set. Now define this X mod G. So X mod G is the set of all orbits of X with respect to action of G. It means this is the collection of all OX where this X is an element of X. Okay. X mod G, it means the collection of all orbits. That's it. Now, one thing to note that like if we want to find a one-to-one correspondence or a bijection between like xg and orbit, so how to do this? So yeah, there is a bijection between xg, that is the set of all orbits, and some subset of x, uh, which we symbolically denoted by this x mod g is bijectively corresponding mm, to this set capital lambda. So this is notation for lambda actually. Why? Because two elements can have same orbits. Okay, it is mm, like it is
Of
written
the
here
following
actually.
numbers n, there does not exist a simple group of order n. 14, 38, 13, 62.
Sorry, are you asking any doubt? Okay. Actually, in condition two, we are taking two possibilities. Like for given two elements, x and y belongs to x. either their orbits are same or their orbits are disjoint. Okay, so yeah, there is a possibility that two elements can share the orbits. It means two elements can have the same orbit. Okay, so like equivalently, we can say that this thing, which is actually the orbit of X, this can be orbit of some X dash also. Okay, so we want to collect some representative for a given orbit. Okay, like suppose this orbit is an orbit for three elements. Try two times. X, X dash, and X double dash. So we pick the element X only. Okay, and suppose this, which is the orbit of Y, this is orbit of some another elements also. So we pick only Y from here. Okay, and from here we pick Z. So in this way, we form a set of X. Okay, so what we are saying here, that we have a bijection between the set of all orbits and a subset of X. Okay, because if the set X is finite, then number of orbits will not be same as the cardinality of the set X always. Okay, that is the cardinality of X mod G. This is either less or this is equal to the cardinality of X. Okay, so if this is if there is a possibility that the cardinality is less, then we can have a subset of X for which the cardinality of X mod G and cardinality of that subset is same. So that is the set capital lambda. Sorry, capital lambda. So do this. Here we choose this lambda, which is a subset of X, such that the cardinality of this lambda and intersection of orbit of X, this is 1 for all orbit of X in X mod. Okay, so using this subset of capital X, we can define the orbit decomposition of capital X. Okay, how? Mm, this X is a disjoint union this time. Disjoint union of orbit of X. Okay. Uh, I will write it again, that X is union of orbit of X if we take X belongs to capital X. Okay. But this is disjoint union. So disjoint union means the orbits we are contributing in this union, they will be disjoint this time. But here we are taking indexing over um, lambda, not the entire X. Okay. So the subset lambda, this is used to define the decomposition of given set X in terms of orbits. And yeah, this is obvious. If cardinality of X is finite, then the cardinality of X will be the sum of the cardinality of orbits, uh, where the summation is taking over X belongs to lambda. Now, if we fix some X in capital X, then orbit of X and orbit of Y, they will be same if and only if Y is same as G dot X for some G belongs to X. Okay, so this is by the definition of group action. So this thing motivates a relation on the set X. How we define that relation? So first, this is the notation for the relation. So relation with respect to the group G, which is acting on the set X. So, okay, now to define this relation. So we take two elements, X and Y belongs to X, and we say X is related to Y if and only if Y is G dot X for some G belongs to G. If Y can be written as this, then we say that X and Y, they are related. Okay. So this relation is actually an equivalence relation. And whenever we have an equivalence relation, we can consider the partition of the given set, which we have already discussed here. Okay. So yeah, whenever we have a partition, we can think about an equivalent relation. And whenever we have an equivalent relation, we can get a partition of the set on which the relation is defined. So yeah, we will have equivalence classes. So this is the notation of equivalence class of an element small x of the set capital X. And this is actually the orbit of X. Okay. And so this is the hint how we can relate the equivalent classes like the equivalence relation and the partition. Okay. And how we define this equivalence classes? The equivalence class of X will have all those elements of the set X which are related to X. Okay, that is some Y will be in the class X if and only if Y is related to X, if and only if Y is written as G dot X for some given like if we find some G in G. Okay, now we have another important term for group action, which is stabilizer of an element of X. See, we have a group which is acting on some set capital X, and we are defining stabilizer of some element of X. Okay, not some element of the group. So, stabilizer of an element. So, actually, yeah, this is obvious because the group is acting on the elements of X. So we can talk about the stability of elements of X only. Okay. So how to define this? So stabilizer of some element X of the set capital X, which is sometimes defined as G of X. This is required if we want to mention the group G, which is acting on the set capital X. Okay. So these two are notations to use to um, denote stabilizer. So this is actually the collection of all G belongs to G such that G dot X is X. It means whenever we perform the group action on this element X, we will get the element itself. Okay. So this is the motivation behind the term stabilizer. That is, stabilizer is the collection of all those group elements which stabilizes the elements of X whenever we perform the group action. Okay. So this stabilizer, this is a collection of group elements. Okay. Stabilizer is defined for some element of the set X, but this is a subset of the group. So this is indeed a subgroup. We can prove that the stabilizer of any given element of X, this is a subgroup of the group which is acting on capital X. Now, a left coset of Gx in G, which is G in Gx, how we define this? This is GH, where this H, this is coming from GX. Okay. So with the help of these, uh, we can define the orbit decomposition again. So as I said that the collections, like here we are taking the elements which are giving us the distinct orbits. Okay, so that is used here. Orbit of x, that is g1x, g2x up to gdx, where this d, this is uh, the cardinality of g divided by the cardinality of gx. Okay, or we can say that the cardinality of orbit of x, this is given by this ratio, but this can be defined if the group is finite only. Okay, so here we define the stabilizer of an element of x. Similarly, we can define the stabilizer of a subset of x. Okay, so to define the stabilizer of a subset of x, we need all those group elements which stabilizes all the elements of this subset T. Okay, that is the stabilizer of T is actually um, a stabilizer just taking point wise for the elements of T. So, okay, suppose we have some non-empty set X on which a group capital G is acting, and this T, this is a subset of X, then we define the stabilizer of T with respect to the group acting capital G. This is the collection of all group elements G in G, such that G dot X is X for all X belongs to T. Okay. Roughly, we can write it as G dot T is actually T, if you want to understand what it is. So this is written point-wise here as we are defining the operation by this. Okay, so this is the way. Okay, so these are stabilizer of an element and stabilizer of a subset. If we have a map pi defined from G to orbit of X, which is defined by this rule, G is mapped onto G dot X, then we can have this pi tilde, which is now defined over G mod Gx to orbit of X. This will give us a bijection. Okay. And so here actually we are using the set uh, capital lambda to define the bijection, because this pi is not in general a bijection. If we want to find a bijection from some um, subgroup of or some part of the group G and the orbit, then we will define this pi tilde for that purpose. Okay. Now come to this theorem, orbit stabilizer theorem. So this says that whenever we have a finite group G, the orbit of X, this is same as, okay, its cardinality is same as the cardinality of group divided by the cardinality of GX. And this is actually helpful whenever we want to find the cardinality of some given non-empty set X. Okay, so um, suppose set capital X, which is non-empty, is given to us, and we want to characterize that set, or we want to find the cardinality of set. So for that purpose, we search a suitable group, say capital G, which can act on the given set X. Okay, we are saying here that G is acting on X. So for that, we want to define some group homomorphism from G to Sx, and that will be useful to characterize the set X. Okay. So here, the cardinality of capital X can be find using the group action. How? The set capital X is actually the disjoint union of orbits of X, where this disjoint union is taking over elements of the set capital lambda. Then the cardinality of X, this will be the summation of the cardinality of all orbits. So uh, how the group G or how the group action is useful here to define the cardinality of the set X, because here we are taking the orbits, and orbits are defined with respect to the group action. Okay, so see here, the cardinality of orbits of X is given by this. So we can combine these two identities to get this. That is, the cardinality of X is the summation of the cardinality of G divided by the cardinality of Gx, where the summation is taking over the set lambda. But here G and X both are finite. Now further we split the set capital lambda in two parts, lambda naught and lambda prime. How? This lambda naught is mm, all those elements of lambda for which the cardinality of G and the cardinality of Gx is same. And this lambda prime, so this is actually the difference of lambda and lambda. So by using this further notation, we can redefine the cardinality of X, which is the cardinality of this set lambda naught plus the summation of cardinality of G over cardinality of Gx. This time the summation is taking over this remaining set lambda prime. Okay, so Gx is G if and only if orbit of X uh, has only one element X. Okay, that is if G dot X is X for all G belongs to G. So if we have this thing, then we say that like orbit is like singleton set, and this is actually corresponding to this set lambda prime. Now, this is another notation, and this notation is fixed point set. Okay. Fixed point set means obviously we are fixing something, but what we are fixing? We are fixing the element of X under the group action. Okay. So, this is denoted by capital X and G over superscript. It means the part of the set capital X which is fixed under the group capital G acting on it. So this is the fixed point subset of X. Symbolically, uh, Xg is the collection of all those X belongs to X for which G dot X is X for all G belongs to G. It means this points X or these elements X of the set X are fixed uh, with respect to all group elements which are acting on it. Okay. So we can equivalently say that the cardinality of X is the cardinality of Xg plus the summation of this part. So this is actually same. Now we define the orbit decomposition of X by this. So if you want to learn these things in detail, or if you want to know the proofs behind this, then you can refer the lecture videos of week 8, which are available on the NPTEL site. Okay. I'm just giving a summary. Uh, Otherwise, we can't proceed to solve the examples. Okay. So that's why the theory behind the problems is useful. Okay, so yeah, this is the notation. That is, the group G is acting on X via this group action tau. So, see, here, this tau is a group homomorphism from G to Sx. So, whenever we have a group homomorphism, we can define its kernel. Okay, so how to define the kernel? The kernel of tau, this is obviously this is a part of the domain group, that is capital G, which is indeed a normal subgroup of G. So, this is and the subgroup of all group elements G such that tau G is this is 1x, that is the identity map on the set X. Okay, or you can say this is the identity element of this group Sx. Okay, which is same as kernel of tau is collection of G belongs to G such that G dot X is X for all X belongs to G. Okay. And see, uh, we have a group, we have a subset, we can define a group action. But suppose by this process, we have a group action on some set X. And what if we have some subgroup of that group? Then again, we can define restricted group actions. So how? So suppose this H is a subgroup of G, then we define the restricted group homomorphism, that is tau restricted to the subgroup H, which is defined from H to Sx. This is a restricted action on X. Okay. Now, what are the applications of group action? So, group action is widely used phenomena in group theory. Which is not limited to group theory. Even you can have its application in further branches like topology, algebraic topology, number theory, some kind of geometry, and so on. So, in today's session, we will discuss some of those applications, and then we will come to the problems based on this topic. Further applications we can discuss in later sessions, or for that you can refer the lecture videos, or you can explore another applications by your own also. Okay, so we rewrite the orbit stabilizer theorem using the like index notation. So this is what this is the index of Gx in G. So the cardinality of orbit of X, this is given by this. Wait, I forgot to write the cardinality of Gh. Okay, but this will be useful. Like the index can be defined only if the group is finite. Now, yeah, this is another thing that for some fixed X and Y belongs to G, if we take Y an element from the orbit of X, that is Y is G dot X for some G belongs to G, then G of Y is a conjugate of G of X. Okay, that is G of Y is Gx, G inverse. So this notation is actually a notation for conjugation. Now, corollary of this, whenever we have X and Y belongs to orbit of X, okay, we will have the cardinalities of Gx and Gy same. Now, these two are examples, or I can say applications of group action. These two are very useful and very important theorems of group theory, and they can be proved using group action. First one is Gall's theorem, second one is Lagrange's theorem. So actually the Lagrange's theorem, you know what is that? Whenever we have a finite group and we have a subgroup of the given group, then the order of the subgroup divides the order of the group. Okay, so we can have an alternate proof of Lagrange's theorem using the group action. Uh, and yeah, the Kelly's theorem. What is this? So, suppose we have a group G, and then we can have an injective homomorphism from G to SG, that is the permutation group of G. Okay, so what does Kelly's theorem say? Whenever we have a group, we will have an injective homomorphism, that is a homomorphism which is 1 1 also, from the group to its permutation group. Okay, so yeah, this is a corollary of Kelly's theorem. If the order of group is n, which is finite, then we can have an inclusion between G to SG. Kelly's theorem is important if we want to figure out the number of non-isomorphic groups for a given order. That is, if some order, that is, if some natural number is given, then how many groups will be there of that order up to isomorphisms? So this is classic problem in group theory, which is not easy to solve. Uh, for some given natural numbers, the problem is solved, but we can't say that there is a generalization or there is a characterization for any arbitrary natural number. Like there is no generalization that if we have a given um, natural number, then how many groups up to isomorphisms of that order can be there. Okay. But this is an interesting theorem. We will address this in further sessions. So, okay, now come to some questions based on the theory we have discussed. The first question, uh, suppose G is a group which is acting on a non-empty set capital X. We define a relation by this on X such that for X and Y belongs to X, we say X is related to Y if and only if Y is G dot X for some G belongs to G. This is actually the relation we defined for the partition of orbits actually. So there we claimed that this relation is an equivalent relation. Now we will prove that the relation is an equivalent relation, and the equivalence classes are actually the orbits of X. Okay, so let's prove it. So let G be a group and G is acting, this is the notation of group action actually, on X given relation is this. This is the notation. On X such that X is related to Y if and only if. So this is actually definition, and definitions are necessary in sufficient conditions, or they are if and only if conditions. So okay, this is the thing. Uh, what we define the relation? Two elements of X. Actually, here we are taking X and Y belongs to X. So X and Y, they will be said as related with respect to this relation if and only if Y is written as G dot X for some G belongs to G. Okay. So first, the relation is an equivalent relation. So when we say that a relation is equivalence, if it satisfies three conditions, uh, if this is reflexive, this is symmetric, and this is transitive. Okay. So if a relation is symmetric, reflexive, and transitive, then we say that the relation is equivalence. So first we check whether this is reflexive or not. A reflexivity of this relation. So for a given x belongs to x, x can be written as identity using identity e dot x for the identity E belongs to G. So G is a group. So obviously there will be an identity, and uh, this is coming from the group action. And we took there that E dot X is X to define the group action. This is one of the condition required. So that's how we can say that X is related to X. For all X belongs to X, therefore, this relation is a reflexive relation. Second is symmetry. Okay, so to check the symmetry, we need two elements. For x and y belongs to x. Suppose x is okay, so this is how we are defining. X is related to y. Then y is g dot x for some g belongs to g. Now, what we are willing to prove, we are uh, trying to do this. Y is related to x also, using this assumption. Okay. Now, as y is g dot x and g is a group, so inverse of this element g will be there. So we can multiply this, or uh, we can perform the group action now using the inverse of this element g belongs to g. So how to do this? G inverse dot y. This is G inverse dot G dot x. See here, don't write this gx or like simply this kind of things, because we are checking in abstract sense. Okay, x and g, they are not same, so this can't be done. We need to use this dot to represent the group action actually. Okay, so yeah, this will be this. Now, now we use the second definition, second condition of group action. This will be G inverse dot Y, and this will be G inverse G. Now, like here, we will use the group operation. We can dot X. So this is the second condition of group action. This will be G inverse Y. This is identity dot X, which is G inverse Y is X, or X is G inverse Y for G inverse belongs to G. Therefore, uh, okay, come to this. We can say that Y is related to X by the definition. Okay. We took X and Y arbitrarily, so this conclusion is true for all X and Y belongs to X. Thus, the relation is symmetry. Now, third is transitivity. That is, the relation is transitive also. So for this, we need to pick three elements in X. For X, Y, and Z belongs to capital X. Suppose X is related to Y and Y is related to Z, then we are checking that X is related to Z or not. Okay. So, okay. Since X is related to Y, we will have that Y is G dot, or say G1 dot X for some G1 belongs to G, and Y is related to X. This will give us that, Z, that Z is G2 dot Y for some G2 belongs to G. Okay. Therefore, Z can be written as G2 dot Y means G1 dot X. That is, Z is G2 G1 dot X. So if we say G is G2 G1, as the group operation on G is closed, obviously. So Z is G dot X for G belongs to G. Therefore, X is related to Z. Okay. So we have X is related to Y and Y is related to Z, and we get that X is related to Z. So we can conclude that this relation is transitive. And thus, this with respect to G is an equivalence relation. Okay. So first part is done. In second, what is asked? The equivalence class of X is the orbit of X. Equivalence class of X is denoted by this X within a pair of square brackets. This is all Y belongs to X such that uh, X is related to Y, or Y belongs to X such that y is g dot x for some g belongs to g, and this is actually the definition of orbit of x. Okay, come to this. Okay. Orbit of x is defined as g dot x. Or uh, write this in this way. This is y. Like all those y which have the form g dot x. So simply we can write g dot x for some g belongs to g. So this is orbit of x. Okay, that is equivalence class will give us the orbit for a given element x and x. Okay. Now come to second question. Let G be a group which is acting on a non-empty set X. We fix some X in T, which is a subgroup of X. Okay. And which of the following is are true? So what we are doing here, uh, we are taking G as a group, X as a non-empty set, and X belongs to mm, X belongs to X, like some element of X, and T is a subgroup of X such that X belongs to T also. Okay. Otherwise, we can't compare their stabilizers. Okay, so we have these things. Then what is the relation between stabilizer of T and stabilizer of X? Okay. So for this, we first recall what the stabilizers are. So we know that what is the stabilizer in G of X? Recall it. Hmm. This one. This is the collection of those elements such that G dot X is X. Okay. And this is the stabilizer of a set. So this is G belongs to G such that G dot X is X. And stabilizer with respect to G of T, this is G belongs to G such that G dot X is X for all X belongs to T. Okay. So first one says that whether stabilizers of T and X are same. Second one says that whether stabilizer of X is a subgroup of stabilizer of T. See, um, stabilizer of X is a subgroup of G, and stabilizer of T, this is also a subgroup of T. So by this, we have two subgroups of G. So we can check whether they are comparable or not. Like this subgroup is a subgroup of this or not, or this is a subgroup of that or not. Okay. So if this one is included in this entirely, then we say that stabilizer of X is a subset of T. That is, sorry, a subgroup of T. So as both are subgroups of G, so to be subgroup, um, being subset is enough. Okay. So first one is whether both the subgroups are same. Second and third, one is a subgroup of another. And fourth one is stabilizer of T is intersection of all these stabilizers of X, where the intersection is taking over elements of T itself. So, see, uh, suppose we have some element Y belongs to X, mm, which is distinct from X. Okay, X and Y, they are not same. And then, like this thing that G dot Y, this must be Y. This condition is not needed uh, for this G to be in stabilizer of X. Okay. Because to define stabilizer of X, we just need to take the we just need to consider the action of group elements on X only. Okay. This condition is not necessary there. But to define the stabilizer of T, um, this is also necessary. Okay. So I will write it combinedly as X is not equals to Y, and this belongs to T, which is a subset, uh, subgroup actually, which is a subgroup of, hey, wait. We are taking X now, so use the proper notation. Hmm. This is not subgroup actually, this is a subset. Okay. Such that G dot Y is not equal to Y. And G dot X is X. Then what we can have? Then say for some G belongs to G. Then this G cannot be in stabilizer of T, but G G will be an element of stabilizer of X. Okay. Therefore, obviously, the first one will be discarded. Like both the stabilizers cannot be seen. It's like we are talking about the possibility. Because T can be the singleton set also. So in that case, like the result is true. Otherwise, we can have some um, Y elements under the set. So in this case, stabilizer of T is not equals to stabilizer of X, and stabilizer of X is not a subgroup of stabilizer of T. Okay, this is true. But again, we consider the definition of stabilizer of T. This is the collection of all G belongs to G such that G dot X is X for all X belongs to T. Say T is Xi, where this I is from some index at T. Then G belongs to stabilizer of T if G dot Xi is Xi for all I, which is like if what does this mean? This means that uh, G belongs to stabilizer of Xi for all I. This means that stabilizer of T is the intersection of the stabilizer of all X in T. Okay. And using this, we can also conclude that stabilizer of T is a subset of stabilizer of X for all X belongs to T. Okay. So which one are true? Third and fourth. So the answer is 3 and 4. Come to the next question. We have two groups, G and G dash, and we have a map F from G to G dash, which is a group homomorphism. Then F is an injective map if and only if the kernel of this group homomorphism is the trivial subgroup of G, that is a singleton identity. So first, let F from G to G dash be a group homomorphism with kernel as a kernel of F. First, suppose F is injective, that is, it is 1 1. That is, for given x and y belongs to G, if f of x is f of y, then we will have x equals to y. Okay. Then what we are claiming that there is no elements in kernel other than the identity. So suppose if possible, some say G belongs to G. Mm, is in kernel of F. That is G belongs to kernel of F. Then f of G, this will be the identity in G dash. Okay. Or we can write it as f of E as like the image of identity of the domain group under the group homomorphism is the identity of the codomain group. This is a well-known result, and we have discussed it in previous sessions. So now, mm, how to do it? See, F, G, and F, E, uh, they are in G dash, or like simply we can apply this. So G is identity since F is injective. Okay, so whenever we take any element in G, we will get the identity. So there can't be any element other than the identity in the kernel of F. Therefore, kernel of F is trivial. Conversely, let uh, kernel of F is trivial. Then we want to prove that F is injective. So we fix some elements X and Y belongs to G with the condition that their homomorphic images are same. That is, Fx is Fy. We have for this, like whenever we have Fx is Fy, then this Fy and Fx also, this belongs to G dash, and G dash is a group. So if G dash is a group, so we can define the inverse of elements there. So Fx inverse Fx, we are multiplying by the inverse of Fx from the left on both sides. So this will be Fx inverse f of y. Now this will be Fx inverse. Okay, since f of x, its inverse is f of x inverse because f is a homomorphism. Okay, this will be Fx inverse f of y. Now F is a group homomorphism, so it will preserve the group operation. So this can be written as f of x inverse x is f of x inverse y. Since f is group homomorphism, that is wait, we're doing this. Okay, that is f of identity is f of x inverse y, or this can be written as f of x inverse y is e dash, but uh, this implies that x inverse y is in kernel of f, but kernel of f is only the singleton e. Therefore, x inverse y, this is the identity. Now, again, we multiply by x this time. X inverse y is x identity. So this will be x inverse, which will be further written as e. So this will be e y as x, or y equals to x, or simply x equals to y. So where we started from, f of x is f of y, and we get that x equals to y. Therefore, f is injected. Okay, hence proof. So next, which of the following is our group actions? First one, the group is defined as GLN-R and X is R square. So G is GLN-R, that is the group of all n by n invertible matrices whose entries are coming from R. So invertible real matrices, we can say. Uh, wait. Let's say for simplicity, we define it. Otherwise, it won't be suitable. Okay. And X is R square. That is column matrices, we can say. X, Y. Such that X and Y are coming from R. Okay. So if this is a group action, then we want to find out um, some map or some group homomorphism from G to Sx. Okay, so we define by this A, X is already taken here, so say M. This is A dot M. For A belongs to G and M belongs to X. Okay, and this is well defined because this A is like matrix of order 2 by 2, and this is 2 by 1. So yeah, we can define it. Now we can see that I2 and M, this is I2 dot M, which is M. For all M, which is actually like this, no? xy belongs to R square. So this is the first condition. And second, A1 dot, or like what will be this? A1 comma A2 comma M. This is A1 comma A2 dot M, which is A1 dot A2 dot M. Now, matrix multiplication, if defined, that will be associative. So this will be A1 A2 dot M. Actually, here the dot is simple matrix multiplication. So we can avoid that if we want. Or like if you are seeing this dot as the group action, then we can also write that this is AM. Okay, fine. So which is basically A1, A2, comma M. Okay, and this is again true for all A1 in A2 in G and M in uh, R square or X. Therefore, we can have a group action on R square via the group GL2R. See, we can generalize this also. Okay, so the group GLNR, this will act onto Rn. Okay, for some natural number n. Second one, G is the group of rigid motions of a plane, and X is the set of all triangles in the plane. Rigid motions, that is, G is the set of reflections and rotations in a plane. Reflection about a line in the plane, and rotation about a point given in the plane by some angle. Okay. So this is actually a group. And what will be the group operation there? So reflections and rotations, they are actually maps. So this will be composition of maps also. So this is the algebraic structure of the group. And what is X? So X is the set of all triangles in the plane. Okay. So we want to define a group action using this group. So this can be thought about uh, mm, like reflections and rotation. restricted for triangles in the plane. Okay, so how we define the group action? Find some phi from G cross X to X by, say, some R, and here we have some T by R of T, we can say. Now we can have another notations also. So actually we have reflections and rotations here. So I'm taking capital R, which will be either some reflection or rotation, and T is some triangle. Okay, so first thing is that if we have the identity, so identity that is we are rotating by 0 degree actually. So whenever we rotate by uh, 0 degree, a triangle, we will get a triangle again, and that will be the same. So this will be actually T, I can simply write for all the triangles. Actually, this E is the identity map on R square. Because we are working on a plane. And secondly, R1, comma R2, comma T. So this is R1, comma R2 T. Here this R2 is a map on R square. Okay. So this will be R1 of R2 of T, or R1 R2 T. So this can be written as R1 R2 comma T. Okay. See, R1 and R2, these are maps. So here the group law is defined using the composition of maps. Okay. Therefore, J is acting on X, let's say. Okay, so both are group action. Answer both. Now come to this. Consider the group GL2R acting on the set of column matrices of size 2 cross 1 over R, that is R square. So this is actually the first part of this, where we have already proved that this is a group action. So here, for this group action, we need to find the orbit of R square. Okay, how to do this? The group GL2R acts on R square via the group action defined as mm, say some matrix A, comma some M. This will be AM, where A belongs to GL2R, or we can write that A is some AIJ 2 by 2 such that determinant of A is non-zero, and M is some XY belongs to R square actually. Okay, now we need to find the orbits of R square. That is, mm, orbits means, say, different elements of R square can have same orbit. Okay, and all the orbits will partition the set R square. Okay, so here we need to find, um, like, this is not being asked that we need to find orbits by picking each element of R square. No, there are uncountably many elements, so we can't do that. But obviously, this is the possibility that for distinct x and y, their orbits are same. So the question is that we need to find those distinct orbits actually, without explicitly mentioning the elements. So let's do it. Actually, the claim is the orbit of any element of R square can be either 1 0 or 0 0. Okay, we can't have any third orbit. Okay, so two orbits, they can be either identical or they can be disjoint. So here we have two disjoint orbits. Okay. Further, orbit of any non-zero element of R square is 1 0 actually. That is this 0 0. This is orbit of 0 0 only. Now let's prove it. Let x comma y, which is not equals to 0 0 in R square. So there can be two possibilities. Case one, um, x, y, and 1 0, they are linearly dependent. Then there exists some non-zero a belongs to R such that xy can be written as a 1 0. Then, okay, this am, or let a is a b c d such that determinant of a is not equals to 0. Okay, now am, which is a dot m, this is given by a b c d. Mhm. Okay, so like, we want to find the orbit. So Actually, I want to do this. I want to find out the possibilities for this g dot x for given g belongs to g. So there we have GL2R as G. So I will pick any arbitrary element in A, and then I will multiply to given element X, which is XY there, and I will find what will be the matrix in that case. Okay, like what is the possibility? I can say like, so this is zero A. I'll say why I'm taking this. Mm, this X, Y. So this will give me AX, AY, or so this is this X, Y. So okay. So this is like this can be written in this form as this XY is actually A10. So the orbit is 10 in this case. Now, second case, if XY and 10 are linearly independent, then we can construct this matrix also. Okay, so here actually this A is non-zero. So that's why like this matrix can be constructed like this because like by this A0, this will be a non-zero and 0A. So this will be linearly independent from the previous column A0. And that's why we can say that mm, this matrix is invertible in um, invertible on R, or we can say that this is an element of GL2R. Okay, so that's why we need that setup. And here, this will be an element of GL2R and XY10 whenever we wish to find it uh, with this 10, this will be, I think I should write this. Uh, X, Y, 10, 10. So this will give me X here and Y here. Okay. Means whenever I add this element from the group on 10, I will get XY. Or if I want to do it similar to this, then like I can write it as 10 here. So this will be A0, or I can say XY also. Therefore, orbit of XY, this will have 10 only. Okay, so whenever we will have any non-zero element of R square, we can get the orbit using this 10 only. Now, if we take this 0, 0, write it column wise, 0, 0 belongs to R square, then for each A belongs to GL2R, A and 0, 0, that is A multiplied by 0, 0, this will be 0, 0 itself. Therefore, we have two distinct orbits, 10 and 0, 0. Okay. So, yeah, there are some more questions, but we are running out of time. So, we will discuss them in next session. So, this is all for today's session. Mm, I suggest you to watch the lecture videos also of this group's this week's and also upcoming week. Otherwise, you can't be able to understand the group action. So mm, that's all for today. We will meet in the next problem solving session on the upcoming Tuesday, in which we will discuss the problems based on week 9's, that is the group action part. Thank you.